Praveen, I will introduce you to Dr. Sushant Banerjee. Now,
Okay.
Praveen actually is the distributor for Synopsys Simpleware software in India, Sushantji, and they are into design, modeling, and also simulation software. And Synopsys Simpleware is actually a US-based company.
Okay, so we'll be starting this technical presentation, and if you have any question or something, probably you can interrupt in the meantime, and then we'll try to answer you on the spot. So just a moment.
Yeah, so my name is Vijay, and I'm here for the presentation today for the Simpleware software. And I'm working as an application engineer for technical support. And our, so we are going to start with the presentation. What is Simpleware and how it is going to implement for the 3D design, and how it makes our work very easy, and what are the various modules including in that, so that you can utilize various modules for your various applications. So basically Simpleware offers complete 3D image segmentation and model generation from ground zero, I mean from the basic, that is import of our data, to segmentation, then pre and post processing, and then creation of a full 3D model based on the various 3D printing applications. We work in the field of clinical as well as materials and manufacturing. So this is totally a clinical application for today's agenda. So in orthopedics and various kind of various body parts that is required for various applications, and that can be analyzed in Simpleware as well. So these are the modules which Simpleware is having for various kind of workflow. That is for creating a 3D model from importing the data. That scan IP is the base module that is required for that. Then if any user or anyone wants to have any kind of meshing part, either it is tetrahedral or hexahedral meshing, or any kind of meshing based on the application. So he can have the FE meshing module. Then for any kind of curved surface that is required for a B-spline method, that is a NURBS model that is used for that. And then we have a CAD and STL design module for 3D printing part or 3D printing purpose. So you can have the surface file in your hand, and you can export this surface file or STL file, we can say, into the relevant format, so that we can have a surface model in our hand for 3D printing purpose. Then we have a design link module that is purely meant for if anyone want to have any kind of work in SolidWorks. So we have the facility to export that particular model into SolidWorks format. So design link module is basically used for that. Then we have some physics flow modules that is used for various kind of flow analysis. Either it is materialistic analysis for having any kind of bone density calculation or any kind of measurement for a particular bone or a diameter of a bone, or something related to a materialistic part, that is used for physics module solid. And flow module is basically used for having any kind of flow into the body part of the application. Let's say if you want to simulate or work in a artery section or a heart flow or a heart model, then that flow physics module is basically used for that, for creating velocity lines or velocity flows or any kind of histogram that is required for that. And then we have some modules for this is a Laplace that is used for heat flow analysis of any kind of application. And we have some automated ortho, yes, cardio and custom modular. This is basically purely meant for the automated section. That is, if anyone is having more number of import data, So he can use this AS Ortho and AS Cardio module. So basically, what Scan IP do is this is purely meant for importing the data and creation of a 3D model, and some segmentation and the pre and post processing is required for smoothing our structure, smoothing our model, and various kind of some other tools is used for making a 3D model. So these are the relevant formats which is accepted by the software, and these are some export format that is accepted. So you can say that ICOM is the standard format that Simpleware is used mostly, and other format is the industrial DICOM format. Then we have JPEG, PNG format also, and we used to provide in the ANSYS, Abacus, MATLAB, COMSOL, Adena. So these are the relevant format that is used for export purpose. For further simulation, if anyone wants, for his particular model that is created in Simpleware, and this is I previously mentioned. This is the FE module that is totally based and used for the application of meshing. That include FE meshing and CFD meshing. So these are the relevant output, or we can say the export format. So in the same way that we have imported, that is the DICOM format, we can export this FE mesh that is created in Abacus, Adena, ANSYS, and some relevant format also is available here. So you can do the standard simulation if anyone want to have any kind of more simulation, then he can use the export format for that. And this is a NURBS model that is totally based on B splines, and this is when we have a NURBS module, then we can convert those NURBS model into CAD packages as well for 3D printing purpose. So we have CAD module that is purely meant for converting your model into the relevant printing form. So it provide the import as well as the export for various design that is used for 3D printing purpose. We have design link that I mentioned that is purely based and is used for SolidWorks. And we can have the export format of our model into SolidWorks format. So this design link is used for that purpose. Now the automated section is here. So the automated ES Ortho and ES Cardio, that is here for these both, or we can say all the three modules is totally based on the machine learning algorithm, and you can see this is the hip segmentation AS Ortho. That the splitting of the mask, or we can say the splitting of each and every section has been done here with the various color. This right femur, left femur, and the relevant hip and the sacrum is just splitted. And we can see this is purely meant for a better visualization of a structure, or we can do various kind of segmentation. You can see the time that is saved by the software by using AS Ortho module is very minimal, and it saves a lot of time as compared to manual segmentation. So this is the application for the automated segment, and this is the AS cardio module. You can see the segmentation of heart, various portions is available here, so that can be done directly. And after that manual, after that segmentation and some pre and post processing, you can continue with your workflow, whatever you want to segment, or any kind of dissection. If you want any kind of measurement is required, then the user can do accordingly. In the same way, the manual segmentation, you can see takes a lot of time for doing any kind of segmentation. Then this particular ES cardio module is used for saving user time. So this is custom modular basically. So this is also one of the portion that is used for measurement of any kind of stats and reports, and model can be generated in. So these are some of our users that is associated with us and using our simpleware software for various kind of applications. That is the medical application as well as the materialistic application. So they are using a simpleware for various kind of workflow. So any question till now, please ask. So I would like to continue, Praveen sir, for
Yes,
your
what you can
question.
do is, Vijay, you can show a small demonstration on live on the software by taking some example. You can show how the software works.
Hello, doctor. Good afternoon.
Hi, Shibu. How are you?
I'm very well.
So
So, how?
I somehow I joined a little late and I
Ah,
missed on that presentation.
acha.
So simpleware, to khair I know about the software, so nothing
Ah,
new about that.
right.
So, because we are working on mimics and then we are also looking at simpleware.
Ah,
So I'm aware about that software.
right.
What is it that probably we would want to understand is purely having the doctor's DICOM, whichever form, whether it's a fracture or a joint,
Hmm.
and then that DICOM to STL, and then doing some form of a preoperative planning.
Hmm. Hmm.
Because Orthotech is planning to go big way into Orthotech 3D,
Hmm.
and that is one strategical aspect, where the software management is to be with us.
Hmm.
So most of the doctors that are known to me, they are pretty excited. So we are like almost now the Orthotech and its 3D is now almost known to almost more than over 1,000 best orthopedic surgeons across India. Because I have spoken to almost in 6 conferences thereafter.
Hmm.
So now, once the project is through, probably what Dr. Mr. Sushant and myself we are looking at is a software that is going to enable the Orthotech to deliver 3D implants or joints, which are very patient specific, so that
Yeah.
we do pre-operative planning on that.
Right.
And then, of course, definitely there will be an onco-orthopedic requirement. We might require to make a pelvic bone, we might require to make a proximal femur.
Right.
So
So,
all those things
yeah.
will require me to understand the DICOM STL to exactly converting that into a model, which would be implantable model for a particular doctor.
Right. So now, Simpleware comes with that kind of an expertise in terms of both modeling, design, and also simulation. And they also are into a, the product, the module
So
will also include.
simpleware is a software which is freely available, no, on the web.
No, it's a licensed platform. Uh, and Praveen, you want to share something, and you have some videos to share.
Uh,
Who
we
No,
can
so
give a demonstration if it's time. Probably we can have a small demonstration of the software.
okay.
Commercial
Okay, so
software has been accepted
doctor,
by a lot
so
of.
doctor has a immediate query. See, Dr. Vikas Jain actually is the medical director with Orthotech. So any questions, doctor? Otherwise, you can ask directly
I
to.
missed on the presentation, so
So what the
I
presentation
just
details?
could see the last 2-3 slides on the simpleware, but they were predominantly the cardiac ones. So I
Ah,
didn't see anything relating to the ortho.
yeah. So can we quickly share that presentation for doctor to get an idea? Praveen?
Yeah, we can do
Yes,
that.
we can share.
Yeah,
Yeah.
please.
Only we will focus only on the orthopedics. That's it.
Exactly. I
Okay.
did
So you
clearly
want to see the
mention.
demonstration of the software, so you just want to have a look at the presentations?
Demo of the software would be better, because that
Okay.
PPT is okay, fine.
Okay.
Yeah.
Okay. Fine, sir. We'll just arrange it. Just a moment.
Uh, So you can take 2-3 minutes. In the meantime, I'll just come back.
Okay, sir. All right.
So I'm there only. Don't worry. I am listening to it.
Fair enough. Fair enough. All right.
The file
demonstration part. So you can see this is the welcome screen for Simpleware Scan IP. So I'm going to take over from the beginning, that is import of our DICOM data to make a 3D model by some segmentation and some processing of the image data that we are going to import. So you can see we have some the import format for the scanned data, whatever we have in our hand, that is MRI, CT or micro CT image data. So you can see this is we have the DICOM image data with us for pelvic section. So I'm going to import that particular data for today's demo, and you can see the relevant stack or raw images format is also available for import our data, and STL and CAD file format is also available. So you can have the import accordingly. So I'm going to import our data. So you can see I'm going to reach that particular location. So I have that location in already selected. So you can see the data has been imported. When you press finish, then so all the slices that is associated with the data is going to import. So you can see we have got three 2D views and one live 3D views, you can see. And this is basically the volume rendering that has happened, that has done by the software for our particular heart tissue that is associated with the grayscales and the scan data. So you can see the volume rendering has been done here, and you can see the two 3D, one 3D and three 2D views over here. And when we scroll this left and right, then you can see the number of slices. You can reach out to a particular number of slices. Uh, so total in the coronal views we have 239 number of slices. In the axial we have 279 number of slices, and the sagittal is consist of 511 number of slices. So overall for this particular a heart tissue, that is our pelvic section, we are going to have the image processing part first, that is cropping of our data. This data is basically cropped from a scanned full body image data that we have. Then we have taken this particular pelvic section from there, and if you want to crop furthermore for this particular slices, then you can do that as well by dragging these white buttons, you can say, or white labels. So you can have the cropping accordingly when you apply this, or you have any kind of dimension in your hand, then you can do by keeping here with the values. So when you apply this, okay, so this is asking for a refreshing over 3D view. So we can have when we apply, then we have our cropped data in our hand, we can say. That is already cropped, so we are not able to see any kind of changes more. Now for creating a mask, that is for capturing all the data that is related to heart tissue, we are going to use and playing with the grayscale intensities. So that is thresholding part we are going to have. So you can see we have three type of options for having uh, yeah, for having our structure in our hand. Just a minute. Yeah. So you can see the histogram part, the profile line part, and the CT preset over here. So CT preset is basically used for various kind of body segments, that is bone. So we can see the bone has been selected. You can change your lower and upper values. One more thing I just wanted to mention over here, that is when we zoom our structure with the scroll button of our mouse and dragging up and down, then it will zoom out and zoom in our structure as well. So you can see when I kept our mouse cursor over a particular pixel, so you can see that is giving the coordinate x, y, and z coordinate of that particular pixel and the relevant grayscale that is attached with. So so you can check whether which pixel you want to have in your hand. So I have already worked on this particular data, so I'm just selecting my values what I am going to have. So you can see in the CT preset we have other structures also for taking other data as well. That is a skin. If you want a skin, if you want fat, then fat can be segregated from this particular imported data. Muscle also can be segregated, and the bone part that is also can be done. So you can see the profile line is pretty same that is compared to when we have, we can say, a particular line when we generate, then the relevant highs and lows of the grayscale is being covered with this particular line. So we are going to have something with the histogram. The histogram is basically having the highs and lows, as you can see, the maximas and the minimas. So we are going to cover this particular capturing the data with this particular. So as you can see, you have to do some manual work for that. You have to spend some time for taking best lower and upper values. So this is just a second. Let me do one 2D and one 3D view for a better visualization. So you can see this is called the live 3D view, and this button is called the fast preview button. So when you hit this particular button, then you are able to see whatever you have performed in the left side, or you have taken the tools from the above portion. So when you hit this particular button, you are able to see the number of steps that you have done. So you can see the mask has been generated successfully from that particular histogram, and you can see some of the muscle part or the soft tissue part has been captured, that has been covered in that particular grayscale intensity. So our work is to remove these small islands, or we can say the noises or the disturbances from here. So this particular, in the image segmentation, this particular mask flood fill tool is used for that. And you can see our source mask, or we can say the active mask, is mask 1 that we have generated. And the output is basically the mask one that we require. We want this particular big mask instead of these small noises that is attached with this particular data. So you can see previously our mask is looking like this, and after applying this mask flood fill tool, we are able to have, just a second, yeah. So we have this kind of cleanness in our structure. So the small island or the disturbance has been gone. Now we can see we want to split our mask. So I'll show you the tool how to split particular region. Let's say the right femur or the left femur. So this tool is called split regions tool. We have the option for adding our regions according to our convenience, or we have the presets already. That is preset is covering so many various applications that is related to the body, that is cervical, spine, or ankle, or hip, or the heart section as well. So we are having our imported data is hip, so we are going to have the hip section. So the relevant portions of that particular hip is has came with the presets of having their own colors for segmentation, or we can say the split. So let me go to the 2D view. So what I'm going to do here is I'm going to segment our data with this 2D. So you can see I've selected the right femur. So when we need to just outline our boundary of femur head for the split. We don't need to be very much precise for that. I mean, approximately we have to make the linings. So as you can see, I'm just making those particular boundaries for the split. And the sacrum part that we need to slice, we need to raise to that particular slice for, yeah. So you can see I'm just taking the random. So after doing this, we have covered all the 5 sections, that is femur, both femurs and both hip and one sacrum. So when I apply this particular tool, you can say the red mask is going to convert into various colors of having specific regions with the split. Yeah. So you can see the pop-up has came and the mask is splitted successfully when we have the fast preview button. So our up-to-date structure will be there. Yeah. So you can see previously the whole mask was red. Now you can see each and every section is having their own color. So that is basically used for the split. So this split region tool is used for that. So for now, I'm going to have one region for applying various other morphological tools as well as some other tools as well as the smoothing filters for creating our structure better. So I'm going to select one region, that is the right femur, for this particular demonstration. So the relevant tools can be used for other sections as well, that is our left femur, right hip, left hip and the sacrum part. So you can see in the left, we can just hit these particular I buttons for activating or deactivating our particular mask. So I'm just having a right femur. So make sure that your active mask should be right femur by clicking on this particular option. So you can see our right femur is having some pose structure, or we can say the spacing is, the gap is there.
Can we do measurements simultaneously?
Yeah, we have the option for measurement, we can say. But after creating our model very much accurate, or we can say something that is required to be very much precise, then we can have the measurement after creating our solid model. This is basically, we have a hollow structure, we can say, because of the scan that we have, this one scan quality we have at the grayscale intensity that is not matching with that. So we have the option, we have the tools for filling these gaps as well. So I'll cover the measurement part after creating
Sure.
my, yeah, my full pelvic, this right femur. So now I'm going to use, just a second. Yeah. So I'm going to use this paint tool for filling those gaps as well. You can see that is associated with our femur. So what I'm going to do is, I'm just closing some of the boundaries that is open, because our structure is not fully closed. So I'm just checking whether some of the boundaries is open. So I'm going to close very random. Those boundaries should be closed so that our mask can be closed from the inside as well. So you can see I'm just taking some random slices for that. I'll use a morphological tool for closing the boundary. So I'm just randomly doing some paint option over here by selecting some of the random slices. So you can see I'm just making sure that our boundaries should be closed. That's it. Okay. So what we are going to do is now. Let me zoom out this first. We are going to use this close morphological tool for closing our inside structure as well. So I'm going to use the x radius pixel, or the intensity, we can say, to 4. Based on our hardware specifications and the complexity of the structure, the time will be taken by the software accordingly. So it totally depends on the hardware, that is whatever we are going to use. So we can see. So in the meantime, the filter is going to apply. Yeah, so some of the portion has been covered. So you can see when I go for the fast preview, you can see some of the changes. Now what I'm going to do is I'm going to use this fill gap tool for closing our some more gaps that is associated with the femur. So the correction has been already done in the femur head. You can see the pixels are getting better. Yeah. So you can see the closing has been done. Uh, the solidification has been done. So one more thing you can do for other cavity, if you want to check, then we have when you click the right button of the mouse, then when we go for let's say the opacity of the structure 0.2, then you can see there is no other gaps or holes that is associated with the structure when we make our structure opaque. And this particular femur is having bone in his whole structure. Let's say if you want to segment your lungs or the liver, so the artery or the relevant part that is associated with that particular organ inside, then when you change the opacity, then those particular organs or the arteries can be visible from inside. So you can see I can change the opacity once again to 1 for creating my structure back. So you can see I have just applied this cavity fill tool is also can be applied for making sure that any kind of holes or pores is not left. So after applying this, so we are sure that nothing is left for any kind of hole. So after this, we can have some smoothing also in our model, so that when we go for any kind of 3D printing and all, so our structure should not be that much rough. It should be very much clean. So when I apply the intensity 1.6 in this particular structure, let's say, you can see the smoothing of our femur is done. So you can see that as well. So the solidification has been done. The structure has been smoothed very cleanly, and now after this, I'll show you the 3D printing conversion or the STL file conversion from here, as we can have a model in our hand from the very ground zero, that is the import of our data, the scan data. I have segmented our data. I have done some morphological tools in that. I have splitted the regions as well. So now I'm going to have our structure that is, we have some more option from here. Yeah, this 3D printing option covers the mask to surface. So you can see, just a second. Yeah. So I've generated a mask that is surface. So this is the surface file or the surface mask, we can say. Now what we can do is we can have, yeah. So we can import this as well. So we have the option for this. For exporting our surface, we can export here, or we have other option also for exporting our this particular surface file, surface mask. So you can see our surface has been generated already. So yeah, we can export this in the form of .html file. So this is our, just a minute. This is our femur. Correct. Let me rename this, and let me save in our, in any of, save here. So our femur has been saved successfully. So STL file exported successfully. Yeah, this is the femur. Yeah, so you can see. So you can utilize this according to your application. So this is the HCL file or the surface file that has been converted and exported successfully. So I'm deleting this for now. Watching this as well. So we don't require this for now. When we drag this particular right femur into model, we have some uh,
Do you want to
various,
you want to
yeah.
do the measurements here only, or you would do there in the STL?
Sir, I'll do the measurement after creating my FE meshing. Uh, then I'll do the measurement from there, or
But
I can do
this,
from here as well. I can
that is
do it.
what. Can you show how you do a measurement here? So
Yes.
suppose I want to know the head circumference, I want to
Yeah.
know the neck length.
Okay. So let's see. I'm just taking the measurement from here as well. So you can see I have selected this view option, view tool. When we do enable, then you can have the option for when we drag these white color balls from top to bottom or from left to right. You can see the structure from the
Yes.
inside. Yeah. So when we have, let's say, you want to measure this head particularly. So we have the measurement tool from here. This measurement option is available with us. So you can see when I select from this particular pixel to this particular pixel, you can see the distance between from here to here, or the diameter, you can say 44.072 mm is the distance of from this particular instance to this
How
particular
do we
instance.
know that this is the maximum dia? Like there has to be a way, where the computer tells us that this is the maximum diameter of the head.
Sir, for the software is basically used for calculating your input, whatever input you are providing, your whatever you are going to select, whatever pixel you are going to select. This particular instant, at that particular instant, that is the measurement can be possible. So the detection part, you can say the detection part. If I'm interpreting you correctly, you want to detect the diameter of a particular instant, but in we can have a check of diameter in a different way. We can have the cut section in with us. Let me make this femur view. I mean the meshed part first. Then I will show you. Yeah. We can segment our head or the femur from segment. I mean, dissect our femur from wherever we want, and we can calculate on that particular area, or we can say on that particular instant by using the measurement tool.
Suppose I want to do a pre-operative planning, right?
Yeah.
So I will definitely, we are the joint manufacturing company.
Okay.
So I would like to know what is the patient's size of the head of the femur. Second, I would like to know what is the neck length. So now what I want you to understand is our application and use to this is not to create 3D models, That's okay. 3D model is fine. But I would love to understand this to give me. So, yes, so this is the way we should understand that we are at the maximum diameter.
Sir, the calculation of that particular maximum diameter by detecting on that particular area. So the detection part is quite impossible, but the manual measurements, or we can say the calculation of that particular volume of that particular area, or the density of that particular area is possible.
So if you segment your head
Yeah.
in around say 8 slices or 10 slices,
Mm-hmm.
so what will happen is it will give us the maximum. So usually what happens is we know from where we want to measure,
Okay.
and what we do is we segment the head into 8 or 10 slices. So the slice which has a maximum outer diameter, the segmentation will be done at the level where there is a possibility of a maximum diameter, right?
Mm-hmm.
However, we don't know which one is the maximum, so you create 8 slices.
Sir, it's I mean the slices from slice mean that I can cut the section from wherever you want.
Yeah. So where you cut that section, and then you keep on taking, you take around 8 such uh, diameters, and the diameter that is maximum is the maximum diameter.
Just a minute.
So that will give us the size of the head actually. Is there a way in which you can pass this head through a ring? So suppose there's a ring of 44, and if it easily passes, can you play with that, something like this?
Uh, I'm not getting, sir, what your exact query is.
So the query is, we have a head of a femur,
Yeah.
and I want to know what is the size of this head of the femur. That's it. How will you tell me?
Let's say we have cut this number of. I mean the distance from the top, whatever the user want,
No, it's
that
a
can be
spherical
shifted.
thing.
Yeah.
See, I understand one thing. You are sitting on a 3D model.
Yeah.
You have a spherical ball.
Mm-hmm.
If I tell you, give me the diameter of this spherical ball at its maximum thing, can you give me?
So the maximum thing you want, that is quite impossible from here, because the detection part is not being done. The creation of a 3D model, and if you want any kind of dissection at anywhere, at any place, or at any distance, that is possible from here.
So now, how will you measure the neck length? How will you measure the head size?
So your
You should
particular,
know. You should
yeah,
know what is the C. That is what I'm trying to tell you. Now you have already removed a part of the head. So
hmm,
then you should be able to make a circle, and you should be able to find out what is the center of this head. And then from center of this head to the center of the neck, if we draw a line, we would be able to get the neck length.
yeah.
Now, from the perspective that we are into joint manufacturing, yes. So on this, we already do this. We do it on an X-ray, and the DICOM itself is in a position to give you the dimensions. So why simpleware should not give?
Sir, these the measurement that I'm going to show you here, this is basically quite possible in this. But I'm not getting your query and the relevant thing that you want exactly. But I'll get back after concerning, and I'll tell you what can be the other possibility as well.
That is because you have not used this for pre-operative planning. That is exactly the reason why you're not getting this. See, when you are
Yeah.
thinking in terms of an orthopedic application,
Hmm.
we are not here to make bone models,
Okay.
right? So
Hmm.
we are not here to use additive layering for purpose of bone models.
Okay. So you want the exact measurement of that particular or
We
the
want to do
maximum diameter.
pre-operative planning. You have a live DICOM image of a patient who
Hmm.
has a fracture on one side. So from the other side, we need to find out what is the size of the head, what is
Hmm.
the size of the neck, because we are going to provide implants.
Hmm.
So that entire concept of using this for pre-operative planning will be nothing but for us to create a set of measurements.
Okay. Okay. So
What
I'll
you
be
are
get.
trying to show us is a simple DICOM to STL conversion, right? We fully understand this, but from here comes the another important thing is pre-operative planning, a
Hmm.
three-dimensional pre-operative planning.
Okay. Okay. So moving on, I'll get back to you. What other possibility can be there for the measurement part, apart from these, whatever I have shown you?
No problem. You continue with your presentation, but
Yeah.
probably that is where the indication for us lies.
Okay. So here you can see the model setup that is associated with the mesh. So we can have the mesh creation algorithm in two ways for creating our tetrahedral element or the hexahedral and tetrahedral mixed element over here. So we can do that as well. With the histogram, with the colors, we can segment or we can check the just a second. I'll show you one more thing. Let's say if you want to find the volume of a particular section, let's say, so this particular section is having this much volume of element that is shown here. Let's say if you want to have the calculation of your volume at this particular point or this particular area, so you can select a primitive from here with the ellipsoid, and you can generate an ellipsoid from here, and you can check the particular area that has been selected by the user, that can be shown. The volume of element can be shown here for that particular instance. If I drag these arrows, so then relevantly the volume has been changed. So these other option for percentage volume as well, in the same way you can
So if you
calculate.
can find a volume, why can't you form pi r square is a volume, right? Mathematically what is pi r square?
Sir, that is basically, so what your question is, sir?
And question is I want to find out a diameter of this head. The
Okay,
diameter.
that I got your point. I'll be get back with your particular query, and we'll try to cover in next demo as well for your particular this measurement part.
Okay.
So these other things I'm telling, these are basically the things that is, yeah. So these other things are relevantly when we have the user ask for calculating the volume, the surface area, and the mass density part of our particular section. So we can do that from here, from this particular options. And when we go for our model, then I can show you one more model on grayscale based model. You can see we have some other materialistic option for creating our uh, particular model. We can have the mass density setup. in the y-axis, the grayscale values, the Young's modulus part, and the PR, this Gaussian ratio. So in what way the user want to have his model in his hand, so he can select that particular instant. And let's say I'm just going to have the mass density part, so I'm just selecting the start and the end values. For that, I'm going to have the positives, and the maximum number of steps you can see here is associated with the end value, so I'm just taking those values as well. So we have the calculations.
Yeah, Mr. Praveen, we have short on time. We also have another meeting to catch up. So my request is, if Dr. Vikaji, if you have any other query,
Nee, nee, nee,
quickly
nee.
we can probably
So
address it.
I have see this is a beautiful way in which he was able to show us a conversion from a DICOM to STL, right?
Ah,
We fully like and endorse all the steps that he has shown as a demo. However, Shibu, you understand where we are going now,
no,
right?
no, I get your point, sir. I mean, the basis and the premises is also going to be pre-operative planning. Where
That is the most
ah,
important thing.
most
I'll be having doctors who will be giving me the
हाँ,
DICOM.
exactly. And उनको दिखाने के लिए पहले एक
Why
मॉडल तो
would why
लगेगा.
would they give me a DICOM? They don't want me to have a DICOM to make a bone model
Exactly,
for them, right?
exactly. So,
They
Praveen, do
Yeah,
you want?
definitely, sir. It's not an issue. Allow me some time. Let me discuss with the team. The diameter of a particular bone or something should not be a big issue, I believe. I'll get back to you. Allow me some time. So I'll definitely get back to you on this. Maybe by today itself, I'll get back to you on that particular issue. Let me
Okay,
discuss
okay.
internally. Yeah, I will. And rest, if you have any questions or specific questions, as per your application, you can let us know. Probably we can try to match that up.
Any other thing that, sir, you need to know, Dr. Vikasji, in soft tissue versus in terms of hard tissues? Other things, I think it's mostly everything is covered. But anything else very specific? Reason is we can quickly go to the other meeting. We have
Yeah,
limited.
so we will also like to see other presentation, not an issue.
Right, right. So, can we? So, Praveen, thank you so much. And maybe, Dr. Saab, this query needs to be addressed. Those are,
We can do that, no problem, sir.
so then that can be done,
Yeah, I will.
and maybe we can probably have that meeting subsequently, if at all, once we have decided on the time and date. Meantime,
Fair enough. No
thank you so
problem.
much,
Yeah.
Praveen. Yeah, thank you so much, Praveen,
Yeah.
for your
Thank
time,
you.
and
Thanks for
also
your time, sir.
Vijay for
Thank you.
your presentation. So now, may I now invite Sibasis, you can click on that particular hand raise bar down, and then you can join him.
For some reason, my camera is not working.
No, no,
Since
fair enough. As long as you can make the presentation, that's perfectly okay.
okay, so I think let me share my screen. Okay, I hope you can see my screen, right?
Yes, yes, yes.
Perfect.
Yeah,
Okay, thank you very much. So my name is Shibashish, and I have Sushil with me. We both work with Altair, and Altair, for those, I mean, you might not be aware, we are into simulation mostly. So basically, we take the loads, boundary conditions. I mean, the way a thing will work, be it a human body objects or be it some mechanical system. We start with loads and then we discretize that geometry and then we try to find out what is going to happen with that load. And then we further go ahead and then ask question like, with this load, with this geometry, whether it is sufficient or should we have to modify this, and if we don't modify, what is going to happen. So that is the very broad high level overview of what we do in different domains. So we are not only in structural, we do electromagnetics, for example, or your X-ray and scanning and all those companies are a customer. We do CFDs, that means all those flows that happens, basically bloods, air, and all those things we can simulate. Then, so all the disciplines we are into simulation, but we also do have some kind of amount of design. So today's focus, I'll probably talk only on or limit only on additive manufacturing, because that is where probably commonality between us and you. And to do that, I'll introduce a platform of software what we call Inspire. which helps design for additive manufacturing. So that means if you know the way that any component, be it your spinal implants or cords, or say your jaw bone or whatever, how much load is coming, based on that the software will help you get the right shape or right kind of shape for that particular component. Why it is important? Because as you know, when you create an implant, it will not be really the human flesh or human body what it was there earlier. So human body or any object in the natural worlds are much more efficiently designed. They can take a lot of loads, but they are lightweight. But at the same time, if you just replicate that with, say, 3D printed thing, which are man-made. So, for example, you put titanium or you put other metals or whatever to replace that damaged portion, and you keep the same volume, same shape. That does not going to work because it will be grossly overweight, and that the rest of the system is not sufficient enough to withstand that. So essentially what I'm trying to say is that you have to smartly design that shape in such a way that it will perform that same work, or it will take the same load, but it will be of different shape. Without, number one, it should not interfere with other objects of the surrounding, and also it has to be lighter, right? So that's the idea. And then once you get that design, then you also have to reconstruct that design. And that's what, if you see this image, there are 6 steps given. The starting is where we are getting the loads. Now it's a by two-wheeler component, but same thing can work for mechanism of, say, your knee joint, or say your jaw movement. So there has to be certain force. So it has to be that body, that person has to withstand. And the second stage is where you are getting the shape actually automatically, and that shape then you are reconstructing. So that has gone in the previous step, and once that reconstruction is done, you are going and actually doing a virtual printing here, where you are understanding that again what you have reconstructed, that will not come as it is after printing, because printing has its own nuances, right? You want X, but you will get X plus delta or X minus delta. So what is that delta that you want to understand? And then you can go back to reconstruction stage and then make sure that you adopt those reconstruction rules in such a way that you get the delta which is minimal than what you wanted, right? So that's the whole story of DFAM. And I'll skip these things. Maybe it will be a little different to connect with you. But what I am essentially trying to say is that what I just said, that basically you start with performance of any component you want to design for 3D printing. Then you design a system which is efficient in terms of both, that is life of its component in terms of applying withstanding the load, and also the mass of the component, right? And then you also take care about the manufacturability part. That means your story does not end till only by creating efficient design. But also you have to make sure that that is not just an art piece. It will be manufactured as it is, or as close as possible to it, what you wanted. And there will not be significant defects being created when it will go to that manufacturing stage. So that's what we call it simulation driven design for manufacturing. Just to give you a little broader example, again, it's not a biomedical example. I'll show you one biomedical example later as well, but this is very common example. Everybody will understand. So that's why I brought this example. This is a two-wheeler suspension system where the blue colored brackets are the one of our interest, to redesign. Now, at present, whatever the design is there, those need to be redesigned much efficiently. That's the idea. Now, what we are doing is that first step, we would like to understand the forces, and that's what we are seeing over here. Through mechanism study, you can understand the forces. If the system is simple, for example, your human jaw, you may not have to do mechanical study. You might already know the biting force of that jaw as much as it should be withstanding, right? So you can directly apply that force as well. And then once you know the forces, you can send those forces to the system, and system will then understand the performance of this component. And then on top of that, you can also tell the system that what is the manufacturing process you are going to follow, because each manufacturing process has its own rules and own rules. So for example, if you go with say LPBA for SLM kind of 3D printing process, it has its own rules and limitation. If you go to say other kind of manufacturing process such as a binder jet and all, it has its own rules and limitation. And if you go to say FDM, it has its own rules and limitations. So all are not same. So you have to, even in the 3D printing, there are goes and no goes for different manufacturing conditions. So you have to tell the software. You may tell the software. If you don't tell, that's also fine. Then it will be a generic design which will come out. But if you give more information to the system, it will create more smarter design which will reduce your late surprise when you actually go to the printer, right? And at the end of the day, you can generate those different concepts based on your both things, that is your application of loads and then your manufacturing process. And this whole thing is done in Inspire platform, which has which should have multiple multiple piece of software to handle multiple things. What you see. So for example, what you saw is first part was mechanism, which does by some MBD kind of code in the backend to extract loads and all. Then second part was optimization. We more technically we call topology optimization, which is done through a module called Inspire Structure. Then there is also a requirement for doing structural analysis to understand that members are not thin, that it will fail and all. So that is done through SimSolid. Then geometry construction, reconstruction and all is done through Inspire Studio. And we do have another module, which I'll come to later, which helps you create the lattice kind of design. And then there are different manufacturing process what you can simulate, including conventional manufacturing process, which may not be interest today, and 3D printing, right? So this is the workflow. You start with your loads, identification of load, and then next is your design space. So design space is nothing but your total available volume to your disposal. For example, previous presenter was trying to create that femur bone, and those whole area could be a design space, and then you can give that load, apply that load, bring to that system, and then it will create the design based on your load and your process input. Process input is your manufacturing process, which 3D printing process you want, right? And then you have to reconstruct it. So we call it detailed design, where our different reconstruction technologies, such as we have polynubs, we have nubs-based modeling, we have lattice modeling, and all those things comes into picture. And then next is, before you say that I have done a good job, you have to also make sure that you technically prove it. So you make sure that you apply those loads again and with the finished design, and make sure that design is not going beyond. So for example, if you take a jaw, human jaw, after you 3D print that person, if he is biting, it should not deflect too much. Otherwise, the whole purpose will be lost, right? Then you will actually go for printing. But before that, you actually do a virtual printing here, because printing itself is a costly, and printing has its own print failure or build failure, especially for the metal, is very, very costly affairs, right? So you have to make sure that everything will go as per plan during building, and after building, it will not see significant distortion that it will distort to something else. Instead of human jaw, it might become a bow, and that might not fit at all. So all those thing you will actually cross-check before you actually fire the print. And then if you are satisfied, you can fire the print and do all those printing thing. For example, you will do slicing, and then you will make sure your machine has certain parameters, and then you will fire the print. In case you see that any of these steps, that is step number 4 and 5, does not meet your requirement, then you may have to go back to either step number 3. If it is a geometry reconstruction related issue, then you can go to step number 3. If it is say more fundamental, such as the design creation related issue, then you can go to step number 2. And even if it is further fundamental, you question the loads applied itself. So, for example, you assume that human jaw will take 10 kilonewton load, but actually it should take 20 kilonewton load. Then you have to go to step number 1 itself and start those loops. So, all in all, it is not a one button click. You have to. There is a circularity in it, and that's why this whole platform works, because it talks with each other very seamlessly. And it is very well quite possible that you come out with design which is as flawless as possible, and then you finally go to the printing. It's a complete workflow. Let's not go too much. And we are into this technology of optimization quite long. I think we are into 30 years and all. With all those fine-tuning options, and also we have a lot of sophistication as far as this technology is concerned, right? I'll skip this. Let me go to a demo on this. This is a prosthetic knee joint, where you are seeing on the top left-hand side is again the identification of the system. How your actual knee works, you are trying to identify, and you are extracting the loads in the first step, and then we are sending that load to your design space. So this brown color piece, what you are seeing, is actually a design space of one of the implant, and then you are sending that load to this, and then let it create the design for you. And from a flat plate, it creates this kind of ribbed design, and then again you are revalidating this whether it over here, and when it finally works, you again revalidate for printing, 3D printing. So you see that there is excessive deformation is happening. Okay, so if I go back over here, so you'll see that after 3D print this guy, this is kind to getting bent too much, and this bend might not be acceptable for you. And if it is not acceptable, you may control it for the 3D printing parameters, or you may actually have to go back to your design stage itself to make sure. I think we have another case over here. So, for example, you see that there is another variant of the same design, and then revalidating it and making sure that all the loads and all are falling in place, and then we are again printing it and ensuring that again all those displacement and distortion are not shooting the limit. We have another technology called. Okay, let me show. I think I am on time. We have so where is it? Okay, some of the other examples where our technology is used. For example, here you can see a medical device. Actually, it's not an implant, but that has been kind of optimized to make sure it is lighter in nature. Here is an implant which is hip implant, and what you are seeing right on the left hand side is how you can create the lattice. I will show another detailed demo of how the lattice can be created. And on the right hand side, what you are seeing is again another kind of lattice generation, but that is much more automated than the left hand side. What you are seeing on the left hand side is a kind of, you are deciding the parameters of the lattice, but on the right hand side, what you are seeing is those lattice are generated automatically by the algorithm based on the loading condition. So that's why you see that on one area, the density of the lattice is much lighter, sparse. On the other hand side, where the load is more, the density is much dense, and it has thicker beams. So that is the difference. Those are the difference between two types of lattice. Here you can see a demo of how a human jaw can be created right from load application. So for example, what you are seeing is, okay. So here, okay, before that, let me just minimize this and put it little over here so that we can understand it better. Here is the design space, the brown color, which was created from the original human body parts. And then what we are doing is we are assigning the loads or applying the loads what is supposed to come. So oops, what is supposed to come over here. So you see that these loads and this red arrows are actually the loads applied. The loads can be very complicated or very simple depending on the situation. Here you see that multiple types of loads are applied. Those small arrows are indicating the loads applied through tooth, and the front also there will be some amount of load applied through your lips and all. And what you are seeing on this 2 point is actually it's holding. So it is telling that it is fixed in this area. And also it is giving there is one plane which is indicating that we need a symmetry. That's not compulsory. If you think that your patient has unsymmetric kind of jaw, that also can be possible. But if you want symmetry, that also can be applied. And then once you do that, what it will do is that algorithm will try to generate those shapes. So you'll see that it is trying to create those member based on the loading condition itself, and where the magic will happen, that you are kind of synchronizing between your natural and artificial world, right? So you are creating a object which is strong, but at the same time lightweight, right? We call it biomimicry, like how bone growth happens. And wherever the load is more, it will try to create those object in a much denser way. So you'll see that this side, it has much denser members, whereas in the center you'll see that there are a lot of space. So once you get that design optimized, then what you can do is you can reconstruct, and that's what it is showing over here, geometry creation. This is one way of creating geometry. There are many other ways. We also saw lattice. I'll also explain it little more detail with another software. But here what you are seeing is we call it polynubs. So there are multiple name of it, some called sub-D modeling, some called free flow modeling, and so on, which is very efficient way of modeling.
Hello.
Yeah.
Sir, can you please able to show us the lattice structure to be done on tubular cup?
Yeah, sure. In fact, I do have an example there. Okay. So let me just finish. I think it will take maybe 1 minute more, and then I'll come back to that. Okay. Is it okay?
Okay.
Perfect. So then once this modeling is done, we call it polynubs, and polynubs is watertight model. So that means you can export it, you can make a CAD out of it, you can do all those CAD operations, you can open it in another CAD software, you can even perform another level of, say, FEA analysis on it. And these are sub-D, so that means each block is activated to edit. So you can edit points, you can edit line, you can edit sides, you can even edit group of blocks as well, and so on. So you can make it hollow, you can make it solid. So there are n number of possibilities. So once that, you can make joint in between, and then once that is done, you can make it bionic in nature, and then you can finally export it, right? And you can then go ahead and do the 3D printing, process simulation, and all those things if you want to do so. There are many other applications where our technologies has been used, right from optimization to design creation. So for example, here you can see one example where design is created for supporting your patient. Here is another example where hip implants has been made. Let me go very quickly to that lattice, kind of design what we are talking about. I think it is over there. Yeah. So there is a tool within our platform. We call it Sulis, which helps lattice creation. The whole purpose of the birth of the Sulis was to see, after seeing the paints in the 3D printing world, and these paints are very common and very costly, what you are seeing on the right hand side of your screen, especially for the metal. There are challenges such as many design iteration required before creating a final production design. Time is time consuming and expensive with metal additive. Traditional CAD tool constrained to deal with rapid design change because those designs are very complex, and difficult, impossible to create the geometry sought after in additive, and difficult and impossible to validate complex AM geometry for manufacturability and performance. So basically, geometry creation, editing, and manufacturing checks. Those are some of the pain. That's where the Sulis was created. And Sulis has two modules, but I think the most important one will be Sulis lattice. Sulis flow is only for Sulis flow is also for 3D printing, but it is mostly focused on those hydraulic manifolds and all those things. So I'll skip Sulis flow. I'll show you Sulis lattice. So this is Sulis lattice, where it has many controls as far as the lattice creation is concerned, because lattice, is beautiful, but it can have multiple parameters, and Sulis exactly help you to simplify those parameters without with giving lot of power. So that means you have many options, but you don't have to be a geek to operate this. All those parameters are just a control panel driven with buttons and drop downs, and you can create practically endless possibilities as far as the lattice generation is concerned. And this is what is our that kneecap what we have created. In fact, we have printed as well. Of course, this is not a medical application. This is crankshaft again, but you can get the concept that what are different possibilities available over there as far as the lattice generation and different types of lattice generation is concerned. And in lattice also there are multiple, you can change the variant, you can change the gradient, you can change the spacing, you can change, there are almost not infinite, but reasonably good amount of control parameters very easily available to users disposal in this software, right? So let me move on and show some of the cases where it can be applicable, right? So I think the most important one for your case would be the implants, which are shown on the third number, which help you to create the design which helps bone growth. You call it osseorientation, and you can make custom implants. So rather than mass production, based on patient's need, it can be redesigned with this software, and then of course validated for manufacturability with our Inspire Print 3D. This is one example. I'll skip it. These two examples are actually, in fact, customer examples where they have created, but we also have some in-house internal test cases. For example, we have this cap over here, which we actually designed and printed. We also have many other things, for example, hip stem and golf putter, brake caliper. Some of them are, of course, mechanical. You might not be interested, but we did a lot of in-house study, in-house design creation, printing, as well as for many of our customer also use that. So, for example, what you are seeing on the right-hand side, bottom right-hand side, is actually that hip implant. But you see the texture over here and the geometry it able to create. And of course, if you create, you can also print it, and then you can use it further. Not only that, we have created some other variant of it as well, which you are seeing over here. And once you create it, creating, as I said, is 50% of your what you wanted to achieve. You can also validate it, and that's what exactly did over here. So we could exactly understand the stress and loads or displacement going to come if our lattice will be like this, which is a very difficult thing to do in conventional FE tool because of the complexity of the lattice itself, because lattice has many surface, many facet, and which exponentially increase the volume of the mesh and all those things. However, with SimSolid, which is another tool in this platform, can be used to understand those interior or intricate details as far as the stress and displacement is concerned. So with that, I think I came to the end. If you have any questions, please do let me know. I think
Can
that's
I
all I
ask
have.
a few questions now?
Yeah, please go ahead, sir.
Okay. You had showed me an Altair femoral stem,
Correct.
right? So that means you must have done finite element analysis for the hip joint.
Correct. Yes.
So do you have any presentation or any slide which shows me as to how did you do an FEA and on what basis did you design that Altair stem?
Yeah, I think I mean, at this point of time, I may not, I don't have, but definitely we have it. And maybe what we'll do is we'll have another follow-up session and explain you thoroughly that how that has been done from end to end, with that, if that makes
So
sense.
can you do a similar FEA for other joints like knee joint?
Yeah,
So
definitely, as long as the geometry and load cases are known for us.
so how do you get that? So I'm an orthopedic surgeon. So how do you want to do those measurements?
Okay. So if you remember in some slides back, I showed that how we normally try to get that. So if I go back to over here, so for example, this is a knee joint. Okay. So now what we will do is let me make it full screen. Okay. So if you see on the top left-hand side of your screen, what we are, we may not directly know how much load is coming on the implants, what is going to be made. But what we might easily know is that how much load overall system is carrying. So in this case, what we are doing is that we are telling that how much load or how much movement this whole knee will have. So if you see that this knee is actually moving over here, so how much movement will be there, and with that, how much human body weight it should carry. Okay, so that might be much easier thing to know. And once I know that, software will give me how much load each implant will carry. So that will be calculated by the software. We call it multi-body dynamics, and that load then we'll use and go ahead with those whole procedure.
So there is no form of a scanner which is available because it will be, see, I'll tell you, if you want to study the joint reaction forces and the joint mechanics, the joint mechanics and joint reaction forces will vary from person to person.
I see. Okay.
Right. So when we are talking in terms of having an implant which is specific, which are patient specific implants, right?
Okay.
It is when you do, suppose it's a hip joint.
Okay.
So 80% of your biomechanics will be common in the entire set of humans.
Okay.
20% of biomechanics will not be common because that person might have a different pelvic tilt, that person might have shortening, that person might have certain form of deformity. So the joint reaction forces for that person will differ from the normal other person.
Okay.
So the FEA in
Uh-huh.
that person needs to be designed an implant.
Uh-huh.
Acetabular component does not require a lattice from the FEA point of view because the entire cup gets into the integration and there is the weight transmission predominantly goes on to the entire semicircular part.
Okay.
Acetabular cup, all you need is to create either a lattice or a trabecule which will only enable osteointegration. Basically,
Correct.
it is
Correct. Yeah.
transmission of the weight bearing point.
Correct. Okay.
However, the other part of the hip joint is the femoral stem.
Okay.
And that is where the FEA, finite element analysis, is very important because it's the head and the neck of the femur where the joint reaction forces are maximum.
Correct.
So when you design an implant, you need to understand that the lattice strength is the maximum in the area where the maximum load bearing is going to transfer.
Correct.
Right? So you can do an FES. I was just asking if you have any mechanism or some form of a scanner, which is a laser scanner. So you can pass through that, which can enable or do a dynamic study to allow us to do an FEA.
Yeah, so that is a good, interesting point, sir. In fact, as far as this that hip implant is concerned, I'm an engineer, so what I could understand earlier is that you have to make sure that your implant is not very strong, so that your subsequent bone will become weaker. I mean, it has ultimately has to help the bone also get strength, right? So that is one. On the mechanical side, engineering side, how we get these forces is through we call it cells, right? We apply this tensor. I mean those load sensor, and from there we get the loads, stress tensor. Okay, and but I don't know how in human body it has to be done. But force is of course accurate
So that
measurement of
is where some part of homework probably Altair and we can do together, because I think there's some research which is also going at some IIT Bombay or a Delhi level, where the biomechanics have to be studied by some form of either sensors in real time.
I
So if
see.
you can do a real time study from where you will get the joint reaction forces, and from the joint reaction forces you will be able to take that data into an FEA, right?
Yeah.
And if you can get that, then and then only we would be in a best position to use your software to design the lattice. Lattice is only then only we can design a lattice.
Correct, correct. You are absolutely right, sir. I mean, input is the most important part.
Yeah.
So
And
definitely, sir, I would be happy to work with you in case you think that that is what we should do. So definitely, we'll be happy to work
so
with you. And
everything looks good, when we present it, but in real life, we know that this is going to vary from patient to patient.
agree, agree, sir. Yes.
However, we have seen the Altair stem, and
Mhm.
it appears very interesting, to see a lattice and a hollow stem, rather than a solid femoral stem. So that is something good.
Great, great. Definitely, sir. Let us know how to collaborate further. I think Sushil is also here. I think
And
he's not able
Banerjee,
to.
Banerjee sir is there, so he'll be able to tell more about the type of FEA studies we would like to do.
Yeah. Good afternoon, Mr. Ghosh.
Good afternoon, sir. Good afternoon.
This is Sushant Banerjee from
Hello,
Orthotech.
sir. Hello.
Okay. The presentation was excellent. I'm really impressed.
Yes,
Okay.
very much. Yeah.
Uh, where are you based, basically?
So, sir, we are wherever you want us to. I am based out of Pune. Sushil is based out of the Bangalore.
Okay. Okay.
So
What
then
we
we
need
have
to do is
yeah,
we need to, have some trial on
Yes.
the
correct,
software.
correct, correct.
Okay. Dr. Vikas is an orthopedic surgeon, and we are collaborating. We are all collaborating together. Let us make a small trial
Great, sir.
based on this. So we understand how, from start from step one to step A to step Z, how we can take it forward.
Correct.
Okay, this is presentation was excellent, but we need to check this practically. Number one. Number two, is your license perpetual or what?
So that can be work out. That should not be an issue. So I think what we'll do is let's first, work together with the foot grounded little bit with you and me, because both are two different disciplines. So then license and all things can be worked out. No, not an
Okay,
issue.
okay. What about the commercial part of it? Because ultimately, it all boils down to the finance part.
So, sir, let me tell you. I mean, I'm not a person who can talk numbers and all, but this whole package of software, whatever I have talked, is based for those for targeting those SMEs. Okay. So we do
Okay.
have customers on for other softwares in large OEMs and all, but this is mainly for SMEs and startups. So don't worry about that.
Okay, fine. So I think we can connect with you immediately and we can start and take this forward as early as possible.
Perfect, sir. We'll look forward to it.
Okay,
Okay.
fine. Dr. Vikas, are you happy?
Yes, yes. So you know what, Banerjee sir, the most important thing is that there is a lot of innovation that we can do here
Yes,
on
yes.
basis of the finite element analysis that we were thinking.
Right.
He has opened our additive layering innovation in the lattice. So there's only one alter stem that we were seeing, but then there are a lot of things we can do once we really get the hold of doing an FEA.
Right, right.
So real time FEA is very important, and then we will sit together and work and find out the way. We have all biomechanical engineers from IIT Guwahati and Delhi and Bombay, so we'll find out a way to do real time FEA.
Perfect, sir.
Sure. Sure. Thank you, Subhashish, I believe.
Yeah,
Thank you very
Shibashi,
much.
sir. Yeah, thank you, sir.
Yeah.
Thank you very much. Take care.
Thank
So,
you, thank you,
yeah,
thank you, Shivaji. It was good. Our
yeah.
entire presentation was really good. Yeah.
So just to add to what Shubhashish just presented, I did have a slides on that, and we also presented in the earlier workshop that we had.
Yeah.
This is all about the complete gait analysis, GAIT, of the motion
Yes.
study that you would do on an human body, and
Hmm.
based on that, you can understand what are the forces generated. There was a very
Yes.
nice case study that we did on an industrial application. If I may probably get a couple of minutes, I'll share you
Yeah,
just two
yeah, yeah.
slides.
Please do that. Please do that.
Yeah,
Shibu, are
please.
you
Yeah.
okay?
Yeah, yeah, I'm okay, sir. We can actually take 5 more minutes.
5 more minutes,
Okay.
Sushi.
Prepare to catch
Yeah,
up with
I'll just
one or
take.
two things.
Yeah, I'll just take 2 minutes. I'll just have two
Please,
slides. Yeah,
please,
yeah.
please, please, please. Yeah.
Okay. Can you see my slides over here?
Yeah.
Okay. So this is a customer of ours who is basically into industrial robotics. They design and develop exoskeletons for various industrial applications. And we had to design and analyze a certain exoskeleton based on a lift capacity that you would need to design for an exoskeleton. So there is a nice video. I'll try to maybe run fast. So here is the person who wants to use this exoskeleton for lifting a very heavy weight in an industrial scenario, right? Um, so this is the problem statement, right? Whatever you see here, the lift capacity is around 35 pounds to 200 pounds. Up to 20x operator strength amplification is needed. It has to be ergonomic, safety first features, and so on. So finally, Nick, we had to design a streamlined mechatronics product in the form of this exoskeleton that you see here, where you need to simulate the human kinematics with motion capture, inverse kinematics and inverse dynamics. Do look at the passive exoskeleton with the human, understand how the electric machine and control system have to be designed so that you make those motions. Okay, because it's a mechanical system here, which is an exoskeleton helping the human body. So okay, God, this is a video. Sorry. Looks like the video is hung.
That's okay.
Okay. Yeah, yeah. So I'll run this video probably. It's a full body, fully powered exoskeleton designed using Orte products. So the whole idea was to optimize the product performance, improve the model interoperability, and see to it that you predict the performance of the exoskeleton before you manufacture it. So as you see here, this is a human body, and what you're designing is this exoskeleton at the back. Okay. So for all the motions that a human body undergoes, as far as lifting that particular heavy weight, and then walking. So while you're walking, you generate a lot of these dynamic forces, right? So based on those external weight as well as the gait analysis that you do on the human body, you generate a lot of these loads. And once these loads are generated, we then take it to whatever Shibashish presented on the Inspire, right? So this initial motion study can be done to understand what are the forces generated, these dynamic forces as you see here, right? At different locations. So here he is looking at the left elbow location. So similarly, you can look at various joint locations. So this motion study, you can do it for a particular patient gait analysis as well. So I thought this
How
could be
do you
of
do that?
interest. Yeah, so this is all based on our solution software called as Motion Solve. The easier, let's say, user-friendly tool that is available as part of Inspire Motion, which Shivashish also presented. This is much more advanced solution, which has a lot of controls and motor design and all that.
So
But
suppose we want
essentially,
to do only hip or and knee, right?
right? Yeah.
And we want to do it for a particular human being.
Okay.
So can we do some form of a research, say, because if understand one thing, one single study on one human cannot give us the right data.
Absolutely correct.
Probably what you need to do is you need to do a target data analytics. That means
Hmm.
suppose I say that a male who is 65-year-old weighing
Hmm.
60 kg.
Okay.
Now, a 65-year-old male who's weighing 60 kg, we have to do 100 such studies.
Oh, okay. I see.
Now,
Okay.
and that 100 such studies for a 65-year-old with weighing 60 kg will give us proper accumulation of a data of the hip joint, knee joint, and this. Now, this has to go at multiple data points. So
Correct.
you can have a 70 kg male who is 75 years old. And
Hmm.
what you can do then is you can then continue to get such data, and from that data, you will be able to create an FEA of hip, knee, and foot, and maybe, because these are weight bearing joints.
Right, sir. Correct.
And that is going to be an enormous amount of precious data, because that study has not been done yet at any
Hmm.
place. You can
Okay.
use a lot of orthopedic surgeons. We can use your software. We can invite someone from the
Hmm.
other technology if you require, or if you and orthopedic surgeons are more than enough, that will enable us then to design implants.
Yeah.
Design
Correct.
implant from the lattice point of view. Now, see, till now we are designing implants which are already there for us, which are very different, solid implants, solid femoral. But if we really thinking in terms of creating the whole concept of Altair is reducing the weight and the use of lattice.
Right. Correct, sir.
And the use of additive layering technology is maximum when you really want to create a lattice, right?
Yeah, I agree, sir.
And that is where I really love the way you have shown us the motion studies. But this is good as far as simulation is concerned here on this. But in the real time, probably when you will be doing at different data specific points, we will really
Right.
get very interesting data points.
I agree, sir. Definitely.
So
Uh,
just to add, Sushil, I think one cost-effective way to handle this, two diversity is to use human dummies, right? So if we can use those standard dummies of certain percentile, we can probably use. I mean, that probably has been used in this simulation. So there
No,
is,
no, no, no. I disagree with that. The dummies will really mask a lot of data. It will not give
Mm-hmm.
you the real. You will have to do it on real human beings.
I
Mm,
see. Okay.
I get it. Okay,
Yeah,
I get
these
it,
are
sir.
yeah.
Yeah.
The excellent presentation, but here it is more of a study. There is a lot of study required on human
Exactly.
beings.
Exactly.
Okay, without
Mm,
human being study, we won't be able to
हम लोग we
decide.
cannot go ahead. हम लोग implant नहीं बना सकते ऐसे.
yeah, right,
Exactly.
right, right, sir.
Exactly. So this is where from where we can collect the data and
Right,
come out with a something called a average kind of a implant and then do the study and without human trials.
right. Sir,
This
just
is
one question. Sorry, sir.
yeah.
Just one question, sir. In any of your studies in the my biomedical field, have you all done any actual tests with sensors mounted on human bodies of different aged patients, where you allow them to maybe walk or run or whatever, and you capture through those sensors some data? Has that been done in India?
No, no, this is not done. This is not
Oh,
done in India. I have seen this in Germany and many places, but not in
okay,
India.
So
Yeah,
you
but
should, in fact, you should initiate that.
gentlemen,
That is what I feel.
yeah, gentlemen,
mhm.
we will need to actually.
Okay.
Sushil, I'm so sorry about
Sure,
this.
sure. No
We are
problems. No problems.
also
Sorry.
catching on the timeline set. Also because Sushantji also has to leave at 5, so we had to schedule it accordingly. I'm so sorry, but
No problems.
Sushil, one important fact that matter that we've discussed here is also it's a research-based activation program. So in
Hmm.
fact, we also are working with 3 of the institutes. Maybe
Okay.
we will discuss it in the course of our time when we can also catch up. Because there is a lot of work now being looked at when it comes to simulation softwares, looking at how institutes can actively take this as a course forward. So we will definitely be working on that aspect also, and I'm sure it could be a fact finding for us to also see that how Orthotech and Dr. Vikas and Shushanji and all of the team members can also actively be involved, because this is exactly what we are doing. With 3D Graphy is already signed up with 3 of the institutes, so we are working on this. So we'll work and take the course forward. Thank you so much, Sushil, and we will
Thanks.
be
Thanks, Dr.
connecting.
Chibu.
That you would want to quickly maybe summarize for this particular presentation, Dr. Vikas?
I think you know what. This is a field of research,
Yeah,
actually. And somewhere in the entire ecosystem, orthopedic surgeons can help in order to do this form of a research, provided there is also a technology company along,
yeah,
right? So like Altair. So Altair is, if they are targeting medical healthcare, if they are targeting lattice implants, uh, then this form of a research is very important, where, as I rightly mentioned, we'll have to do in age groups, we'll have to do in different weights, and then only we will be able to come out to an inference after doing a good amount of data analytics, that what is going to be the right lattice implant. So just doing a dummy simulation and doing a dummy testing will not help, because we are actually in the real time world. Banerjee sir will also tell you, all these things have, there are enormous amount of data points that undergo, and then there comes a design part. So these femoral stems or acetabulum, these all have been designed after doing so much of research.
and I think that is where Doctor, even customized solutions that we are looking at, that is even one step ahead. So all of these technologies can definitely assist and help us,
All
provided we have
stakeholders will have to come together.
come together. Very true.
Altair as a one part of the software and technology company, orthopedic surgeons, and then medical device like Orthotech. All of them are working together and probably doing a good 6 months to 1 year of a research, getting huge amount of data points, and then drawing inferences from a good data analytics, which will be something. I don't know. It's going to like be a very disruptive thing.
Yes, yes, yes. Thank you so much, Doctor. Thank you so much, and thank you, Sushil, and thank you,
Shibishish,
Sibashish.
yeah.
Yeah, thank you
Yeah.
so much for your time, and also Now we will like to dwell upon the next presentation. May I now invite
Thank you so
Mr.
much. Yeah.
Satyam Kumar. Satyam, you can actually raise your hand for you and your team to join in. Anil is also, I can see Anil also. So both of you can raise your hand.
Hello.
Yeah. Mr. Kumar, you can start your presentation.
Okay. Thank you. Thank you, Dr.
Before
Shivu.
that, let me introduce you formally. I'm so sorry. There is a cascading effect in terms of time, but sorry
Hmm.
for that, and we will quickly start. I have Murli also join in. Uh, Murli and Anil. Anil also. Anil, the invitation is sent to you. You just need to click on that. Very good afternoon. So let me introduce ourselves. We are 3D Graphy, as you know, and let me introduce you to the key respondents today. We have Mr. Sushant Banerjee from Orthotech, who is the founder of Orthotech India Private Limited. They are actually an orthopedic implant manufacturing company, and they've been, actively, offering. Orthopedic implant solutions in modular implants for the last 35 years or plus. And now they've also setting up a 3D unit. They've already been able to procure 2 machines in polymer, and they are also looking at substantiating it through creating a proper setup with even metal going forward. So they would also need software in terms of as a part of their process in terms of the development, and also ensuring that the end user gets the solution customized. So customized solution is an important aspect for activating services and business. And then I have also Dr. Vikas Jain, who is the medical director with Orthotech India, also responsible for identifying these solutions and taking a call in terms of taking the course forward. So Murli, you may so also Murli is the sales director with ANSYS. ANSYS is also into simulation software, and they are one of also a key respondent now to start with. So yeah, so who will be the so Murli, who will be the the person to make the presentation?
So Dr. Shibu, Satyam would be presenting it. Can you let him in?
Yeah, yeah. So he has to raise the hand. I just saw it, and I have also invited him. He just need to click on the button, and then he's in.
Okay.
Yeah,
Hello.
he's
He's
in.
in.
I can see it. Yeah,
Hi, Dr.
yeah,
Shivu.
yeah.
Good evening, everyone. Can you hear me?
Yes,
Yes, yes, yes, Satyam. Yeah.
we can hear you, Satyam.
Yes, Satyam, you're good to go. Thank you.
Satyam, I can see. You can continue.
Okay. Thank you. Thank you, everyone. Okay. So, hello, everyone. A very good evening to all of you. My name is Kumar Satyam, and
So,
I'm from Ansys, India. So, in
welcome,
this,
welcome.
thank you, Doctor. So, in the next 1 hour, I'm going to talk about additive manufacturing, its role in healthcare, with some case study, and also I'll be talking about the role of simulation for additive manufacturing in healthcare industry. So I'll not go very deeply into the introduction of additive manufacturing because all of us here are well known to what is additive manufacturing. Still, I'll brush up with just one slide. So additive manufacturing refers to the technology in which a structural 3D component is made by adding materials successively. Yeah, so how I actually plan this session is that I'll talk little bit about additive manufacturing. Then I'll talk about ANSYS solutions for additive manufacturing, especially the manufacturability part, that how we can address the different issues. And we'll take then I'll show you a few case studies where we have done some work related to optimization, like lattice optimization, and then later I'll also show you that how do we successfully manufacture these lattice optimized implants without much iteration by simulating the this additive manufacturing process. So those things I'll be covering up. So, but before that, let me give you some highlight on the different benefits of AM medical implant. So the first one is the ability to create a patient-specific implant. So you know that with the traditional or conventional manufacturing process, it is very hard to manufacture a patient specific implant, and there is a need of patient specific implant because we know that the anatomy of a person is different in every case. So there might be some scenarios when we want a patient specific implant, but as these implants are not very easy to manufacture using conventional manufacturing process, so that's a barrier. So that barrier can be avoided by using additive manufacturing process. Then the second advantage is your part consolidation. So with additive manufacturing process, we can consolidate many parts, and we can create like we can consolidate multiple parts to make one part. So that is an advantage with additive manufacturing process. Then the third one is the ability to manufacture complex design, which is impossible with your traditional technology like machining or casting and so on. Then the next advantage is to produce the parts as needed. So here the lead time is less compared to your traditional manufacturing process, because we don't have to look for suppliers in different part of world, and I mean there's a lot of lead time involved with the traditional manufacturing process that can be avoided with AM technology. And also we can reduce the time to market, because the delivery time with the AM is less compared to your traditional manufacturing process like casting and CNC machining. The other benefit of having a AM medical implant is that here we have more freedom to consider the different biocompatible materials. So we can also work on new material grades, and we can use those material grades to manufacture AM implants. Now, talking about the different benefits of AIM, we do have a lot of challenges also involved with additive manufacturing. On the AIM process related on the AIM process type, if you talk, we have different issues like aborted jobs from parts or suppliers. So there are many issues actually happening on the printer when you go for printing a part, like blade crash, gas flow or powder control issues, then multiple lasers and recorders type. So because of all these things, there is a lot of issue while actually printing the parts, which reduced in your fail bill. So with aim simulation, we can avoid this fail bills, and we can produce or manufacture parts in very less iteration, or maybe in the first time also. Then on the medical implant side also, there are challenges like osseointegration, stress shielding and bone wear, then printing of porous materials and so on. So these can be handled with additive manufacturing or with the help of simulation, to be more generic. So ANSYS, so how ANSYS simulation assists here is that with ANSYS simulation, you can optimize or design the different implants. So you can introduce things like lattice optimization to further make your implants more efficient and more lightweighted, as well as to match the stiffness with your bone. So those things can be achieved by doing the lattice optimization here. And also with the capabilities like DFAM, we can print these implants successfully without much iteration, which will reduce the cost and the time to market. Then we can also use the manufacturing simulation of additive manufacturing, where we have different where we have different tools to optimize the orientation, come up with the right support structures to predict the residual stresses, distortions, build failures, part deviations, and so on in the manufacturing in the process simulation part. And later with ANSYS solutions, we can also analyze the performance of these implants. So we can predict the performance and strength behavior before implementation by doing the FE analysis on these implants. So this is one image I got here, where you can see that how the topology optimization has been done on this implant. and later this is also validated by doing the FEA simulation on this implant. Now talking about the ANSYS additive solutions. So ANSYS additive solution is offers a very broad and comprehensive uh, simulation solution, which starts with your design for additive manufacturing, where you can do CAD modeling, you can do topology optimization, lattice and lightweighting optimization. Then we have tool for build setup, which will help you to optimize the orientation of your part on the build plate and come up with the right orientation and support generation. Then we have the process simulation tool, where you can simulate the AM process, basically the metal additive manufacturing process, to address or to see the residual stresses and understand the distortion during the print and avoid your printing defects like blade crash, high strain, and so on. Then we do also have advanced tools for material analysis, where you can predict the grain structure. You can see the porosity of a printed part based on the different process parameters involved in AM process. Then we have tool for data acquisition and management, which will help you to trace and track the data generated during the AM process. And then we have the part qualification tools, which can be utilized for doing the design validation and doing your structural and thermal and other type of FA simulations. uh, Now I'll take you to one case study, one case study of a femoral stem implant, where I'll show you that what all we can do using the ANSYS solution. So hip implant or hip surgery is a very common type of surgery which is performed like every year. So an estimated 2.5 million people in US have undergone total hip orthoplasty or total hip replacement surgery. So this is a very common type of surgery. So that's why we have taken this example here, where the hip implant is made up of Ti6Al4V alloy. And what we have done is that we have taken this traditional implant here, which is solid here, and we have performed the FE analysis on this, and we have optimized this implant to have lattice structures here. So I'll show you that workflow here. So the workflow starts with your material analysis, then your initial design, where FE analysis has been done. After this FE analysis, based on the FE analysis result, we have done the lattice optimization, where you can generate the different type of lattices here, which will be helpful for your bone in growth and also for your stress shielding. And then we have validated this optimized design, whether your optimized implant is meeting the product performance or not. So we have validated here by doing again FA analysis, and from here onwards we have taken this implant for your aim simulation, where first we have done the build setup study, where we have done the different study for your orientation of this implant on the base plate, and we have generated support structures. Later we have done the build simulation. So here this build simulation has been done to understand the manufacturability of this AM implant here, or the femoral implant here, where we have studied things like residual stresses, your distortions, and so on. And later we have compared this printed implant here, or the simulated implant, with the original implant, and we have seen the tolerances, that how much it is deviating with the original or the designed implant. And at the end we have done a validation here. So we have applied some load here, and we have seen the fatigue life of this topology optimized implant. So this is the aim workflow what we have done. So from the next slides onward, I'll go to each of these steps one by one, and we'll show you that what we have done. So for the material side, we can use you can use our Granta MI tool, which is a dedicated tool for materials here. So Granta MI is a tool where we have we have a list of or database of materials here. So you can find all the medical grade materials there. And also this Granta MI tool is useful for tracing all the material data generated during the printing process, and also the different data from the designing part of the implant. Now, in the next step, we have done some material analysis on this data, where we have done the study finding the right melt pool dimension for the printing process. So we have different parameters from the AM printing machine side, like your laser power, scan speeds, and so on. So these scan speed and laser power will give you different kind of microstructures, different type of uh, your mechanical property based on that what material, what machine parameters you are using. So it is very important to identify the right set of your machine parameters before going to the printing, so that you can have a good mechanical property of your 3D printed part, as well as you have the right microstructures. So here in this material analysis, we have done this study, which will help you to understand the porosity of your printed part and the microstructure of your printed part. So from there, we got to know the best process parameters that can be used for the printing process. So that study has been done before designing the implant on the materials. Then in the next step, we have done the geometry reconstruction step. So we have this STL here of the bone, which doesn't look very good here. So it has got some defects. So we have a tool for STL repair uh, in our space claim tool, which is dedicated for operating on the STLs only. So here you have different options like shrink up, then removing the sharp corners, making the steel smooth, converting the STLs to solid geometries. So all these things you can do here very easily by just a few clicks, and you can make your STL into a 3D model, which can be later utilized for your designing purpose as well as your FE analysis purpose. So this has been done here with this facet options present in our geometry tool. So you can see that this STL has got some defects at these locations, and those are corrected by this auto fix option here. So just by one click, the software will remove these defects, and it will give you a nice smooth STL, which can later be converted to a solid by this auto skin feature here. So we have converted the bone into a solid model here, a solid CAD model here basically. And then first we have done a FE analysis on this femoral bone and on the implant. So for the femur, we have given the bone material properties, which is basically taken from this Granta MI tool, which is for the materials. And then for the implant, we have used our Ty6 material, which is there in our database. Then we have given some loads and boundary conditions, and based on that, we have performed the FA analysis to see the stresses and the deformations on the implant and on the bone structure. So based on these loads from the FE analysis, we have done the lattice optimization here. So we have set a few constraints here, like minimize the mass, and we have set the response compliance less than equal to this value here. Uh, so compliance is basically a measure of stress shielding in analysis here, and we have given some inputs for this optimization here, lattice optimization here, that what is the size of lattice and so on. And based on that, based on these constraints and these inputs, the lattice optimization has been performed here. So this is the workflow. That is the first step. We have done a static structural analysis, and based on that, we have done the lattice optimization. And this lattice optimization results are used to recreate the lattice here. So based on this lattice density here, we have used this lattice density, and based on that we have created lattice structures like here. So you can see here that at some places it is solid, and at some places you have lattice. So based on this is based on the density what we got in the lattice optimization analysis. Yeah. So then in our CAD tool we have created this lattice here. This is again very simple few click solution. So by that you can create this lattice optimized implants. Now in the next step what we have done is that we have validated this optimized design, this lattice optimized design we have validated here. And we have done the same FE analysis here. So we have applied the same loading conditions, same boundary conditions, and we have performed a similar kind of FE analysis here. And based on that, we again saw the stresses and deformations in the lattice optimized implant, and we compared with the actual one, and we see whether those are meeting the actual values or not. And if it is in the limit, we say that our design is safe, and we go for our further steps.
So just to add to Satyam's workflow, what he's showing. So the basic idea behind all this is that all the complex workflow is there in the same tool, and you don't have to leave the GUI to work with multiple tools. So it saves a lot of engineering time and a lot of manual errors that can happen. So
Can I
that's one of
ask
the
a
biggest.
question here?
Yes,
Hello.
Yes, sir.
yes.
So, since we are already Orthotech is into the hip implant manufacturing since our 25 years. Suppose on the basis of the lattice femoral stem that you are proposing, I as an orthopedic surgeon would like to ask you a question as to how would this stem uh, be able to fulfill the FDA compliances, because that is very important. Ultimately, the doctors will ask also for certifications, also for compliances, and
Yes.
whatever form of once you change a design, you're not changing too much of a design, you are innovating the whole femoral stem, right?
Mhm.
So once you are innovating it, you are trying to create a lattice. How do you get this as an FDA approved product?
Yeah. So on this example, I think Satyam, you have the ISO certification that was in the part of the simulation, right? So,
Right, right,
Dr.
Anil. So
Vikas, what we have to do,
yeah,
we have to follow all the loadings and the constraints FDA has put in place for these implants, and that is how we actually uh, make sure that it actually satisfies that. And as far as FDA approvals are concerned, we are working with FDA on some of the, for example, final implant. So we are directly working with FDA and multiple tools to approve the whole digital process so that it doesn't need to go through uh, physical prototyping once that process is done. So if you digitally validate it, they will accept it. So this is we are not showing here that example, but we are working with FDA on such examples, and that is something which we have to work on individual things like femoral and others.
Yes,
Sushant,
thanks, Anil. Dr. Vikas, this is Murli here.
yeah,
You
yeah,
have very valid question, and fortunately, we are in a time when FD is also outward looking now. So we have a team in ANSYS which closely works with FDA, and
okay,
one of the things that we have actually established and proven and acceptable by FDA is like Anil talked about the whole digitalization process. So any product that is repeatable and out of patent, that means the product which has already been established by FDA, approved by FDA and being in use for a long time. Minor changes, minor changes in that or off patent product when it is generalized. If the digitalization shows the same kind of results or these simulations give the same kind of trends or results like what was done during the patent approval process. These are accepted. So with an Indian company, we have already done that. It's not for implant. It is basically for a respiratory device. I will not be able to name it, but it was for a respiratory device. So we actually did the simulation of the whole respiratory tract with that device, and showed that this design actually maps to the original field trials or trials that were done, which was submitted for FDA approval. So when we come to the implant, so if the implants are already been approved with those minor modifications, with multiple simulations, we can actually go to the FDA for approval, and they are open to evaluate and consider these as a as close as human trials itself.
I fully agree with you, Mr. Murli. We are talking about the predicate products in the market. Okay, and slight modifying here and there, and then working on the simulations from ANSYS will give us a good result. Definitely is there. But when we are talking about the additive manufacturing will be a new thing in India, and this trabecular structure femoral stem will be definitely a new product. So suppose we have been designing a Muller stem which is already existing in the market for last 20-25 years. And if we add an additive layer to it, like the trabecular structure on the periphery to give the bone, bone in growth, can that be validated by ANSYS? From the software point of view.
Plus additive, with additive, we can actually validate and give those digital solutions. But one thing you have to, sorry, there's a lot of disturbance at my end. Uh, but with additive, we will have to prove with certain case studies and studies. It's not going to be that you submit your additive simulation studies and they approve. We will not only have to get the additive process approved digitally, but also the modification that you want to do module to module or patient to patient. So once it's going to be an exercise, because with the Indian company that we work, it took about a year and a half to establish with least human trials or no human trials. So this is a process that you will have to go through, and we can be part of the journey with our team who works with the FDA team in both US and in Europe.
Eh, Murli, can I add a point here, a small point? So,
Yes.
uh, so adding to the Murli's point, so we are quite aware of three testing aspects, right? In vivo testing process and in vitro testing process. It's been there since long time by the FDA. FDA is a general experimental process people used to do. Nowadays, I think in recent past, people are talking about another testing methodology, which is being approved by the FDA, which is called as in silico testing. So in silico
Right.
testing has a methodology of including simulation and software for doing these type of simulations, be it a drug delivery test or be it a implant testing. So this is being approved by the FDA and many of the trials are happening. But I agree, additive is a new process which need to be validated. But because already methodology is being already validated by the FDA, if we can prove some of these aspects can be done through this additive manufacturing approach, definitely I think it should not be a problem, but you can avoid many physical testings and that can be approved by the FDA.
Yes, Mr. Kumar. In that case, we will be needing some case studies from your end to justify that. If you have some case studies in orthopedics, that will be a great help to us, because that is where we will be using those documents as a precursor to our future movement.
Yes, we
Yeah,
have some case
that's a
studies available. Sorry, please, Murli.
Yeah, sorry, Dilip. We have case studies, but as far as the FDA approval is concerned, I do not know if the NDA may, the non-disclosure agreement we have, we may be able to show that, but we will check with that. But one important thing that I want to tell the whole team here is, if at all you decide to explore this way, the additive way, and go forward, you will also be brought in touch with our team. There is a Dr. Marshall who sits in US. He will also have interaction with you and also understand and guide you on how these things can be done because he's part of all the FDA committees. He's part of he's an ANSYS employee, but he works closely with FDA. So as a technology vendor, we can actually get those things also connected, which will help you to understand what is the right process to get the FDA certification for additive and for also the other implants that you plan to do.
I
But
have a suggestion, Murli, if you can do that. Since you have a US partner, companies like Depew, Medtronic, Stryker, and Smith and Nephew are already into additive layering. Uh, they
yes,
are already into additive layering as far as hip and knee is concerned, and these companies have not got their products in India, but they would definitely be having those products which are US FDA approved. So, can they have a look at that?
yeah, that's what I said. Also, being in India, we may have limited view as far as Medtronic, Striker, and these entities on the additive. But yes, my global team may have because Striker and Medtronics are our global users. In fact, Striker in Delhi uses a lot of these tools, but that's more from design and development and functions point of view, not from FDA point of view. So we will have to bring in our global expertise in this, and I like that idea. So what we will do is with whatever background we have, we will have a briefing session with our team, and then if and when Dr. Vikas and Sushant are available, we can align a call and maybe a first session of interactions and sharing of information that can happen, and then we can take it forward. But all the companies, I think J&J and Johnson Johnson, Stryker, Medtronics, and what was the fourth company you mentioned, sir?
Smith and Nephew.
Yeah, this the fourth one I'm not aware, but all the other three are using.
Stryker, Smith and Nephew, all of them have got additive layering technology with them. They are doing a lot of work in making implants out of additive layering. And however, the designs and those implants are limited to their own country. They are not yet coming to the western, the eastern side. However, if you have a US counterpart who is into additive layering, he'll have a very good idea about all the things that are happening there.
So is the question more on the FDA approval process and its
No,
challenges, or it is about additive?
it's very simple to understand that if they have something which is already US FDA approved, the things get very simpler for the orthopedic surgeons.
Yeah, I understand because we did work. We did work with, as I said, not on the implant side. They follow these V&V 40 regulation guidelines, and we are very happy that now they have received the FDA approval for their device. So I don't know which regulation the implants follow, but let me see if I can arrange a call which can be a call with our there are two gentlemen in Europe and US, Mark Horner and Terry Marshall. Myself, Anil, and Dilip will give him a briefing about the discussion that we had today, and maybe then set up a call to discuss further. The intent here is to just get an understanding on the both sides whether it's a way forward that Orthotech wants to explore.
Not only that, not only Orthotech, because Orthotech is going to be the first company in India which is going big way into the hip joint and manufacturing. And acetabular component and femoral stem are going to be the prime things which we are going to print on our metal printer. Now, there has been certain designs which you have showed, and that is particular to a femoral stem. I have seen femoral stem with lattice, and I have seen femoral stem with trabeculae. Both are different. So,
Okay.
the femoral stem with lattice, which you are trying to show, uh, what are the compliances that it will need to take it to market is what is important to us. Making the femoral stem with lattice once the STL is ready and the type of dynamics that you are trying to show us, it's not going to be difficult for us.
So, Doctor,
You're absolutely right. You're
may I
absolutely
just
right.
share my insights here, Doctor? Because, in fact, as we were actually dwelling upon this particular formation of these approvals, we have IIT Bombay already got, their CDSCO and their approvals for even orthopedic implants, if you know. They are also into metal implants. So what I've been told is they have already got an accordance. So we can probably take that as one good reference to take things forward, Doctor. So that is should not be a that should not be a challenge. So since we are actually taking the same path, IIT Bombay is already doing it. They've already got the requisites approvals also. In fact, I wanted to speak to Dr. Sushant and also you to take things forward. But this only happened yesterday. We had a
Oh,
detailed discussion. Yeah, it's already approved. So it's already been approved by CDSCO. So
oh,
CDSCO, is it? And now, when it comes to simulation softwares like these, this is only making our job more easier, especially
exactly.
with their softwares being already FD approved. Uh, Many of them are already got the accordance. What I'm also told is till date, head and neck was being used very, very actively, PSI. Orthopedics, I think ours will be one of the private state, organizations to start one. Would be a great idea. So I think keeping all that in mind, only keeping all those check measures are also good for somebody like a private entity. But institutionally, government IIT is a government institution, so that actually they've already got the pathway is set and ready. It will not be a challenge. So. Doctor, we can connect, doctor. That's not an issue. I will share some of those inputs, maybe because that will have to be closed doors. As Murli also mentioned, there is also an NDA, a lot of we can work towards that.
We
Really,
are
we have a team here.
so we are very sure about making our hip implants, which are highly innovative. The only
Yeah,
thing that is going to be for all the orthopedic surgeons is the compliances. So once we show them the compliances, it's not going to be beautiful femoral stem designs which have been shown by Kumar here, and we have also certain innovative acetabular components which we have been studying since last 6 months. Printing them will not be a challenge at all, at Orthotech,
exactly,
right? The
exactly,
only
exactly.
challenge that would be there is then the doctors are going to ask about compliances, right?
Yeah, so our paperwork needs to be ready, sir.
Exactly,
I
exactly.
completely agree with you. So I think that is set. It's all in place. So we also built that small consortium now within the approval. In fact, if you remember when I spoke to Dr. Jayesh also,
Uh,
Jayesh comes from a different degree of approach. But this is another team that we are also working very closely. So we have four teams. Since you're also one of the key respondents from
now,
IT, when you come next time, we will also meet up.
now,
We
Shibu,
meet them.
what? We are ready to go to market. Understand?
Yeah,
That time
yeah.
was a time even we were just speculating, okay, should we be doing into 3D or not? In the last 6 months,
Yes, yes.
a lot of work that has happened with me and Mr. Banerjee, and now we are ready to go to market.
Right, right. Very good, sir. In fact, I have also said I will meet you. I will speak to you subsequently. We also have some of the accorded approvals from the Association of Healthcare Providers of India. What we are
Yeah.
doing is we are setting up these labs, and this will also be connected and linked to various centers of excellence. Ours being one of the center of excellence in terms of offering metal implants, because the
Yes.
hospital would not have that kind of a metal setup.
Metal
They are
implant
not
printing is
fortunate.
not
Yeah,
possible
yeah.
by everyone.
So exactly. So there could be a small channel of having a lab setup, which is already that we have instituted. We will be starting with 90 hospitals, sorry, 70 hospitals to start, and slowly we'll build on that. So these centers are where the procurement will happen when it comes to metal implants. But the hospital will be more keen for pre-op requirements in terms of planning and surgery. So we can work in that kind of a module also. We'll discuss that separately, sir. So
But
I will ask somebody.
ANSYS has a beautiful presentation because they have their own USP as far
Yeah,
as biomechanics is concerned. So our interest with ANSYS will always be there with Mr. Banerjee, myself there, and with Mr. Kumar, Murli, and Dilip, all of them there.
right.
But because biomechanics is going to be our main part and stay for our innovation. have certain more innovative designs. Unless and until we get the biomechanical studies, we'll not be able to take it ahead.
Yeah. Okay, so gentlemen, so doctor, may I request the presentation to start so that we can
Yeah, sure.
continue,
Please,
and
please.
then we can. Yeah, so we can start the presentation. Thank you.
Yeah, thank you everyone for your input. So I'll resume from here.
And Satyam, just very quick. So let's show the examples and capabilities and have the discussion going. Uh, I mean,
Yeah,
we
All
can
right
go
avoid,
then.
into detail
yeah,
initially.
Kumar, avoid the workflow in the sense how they have to take the data from one software and avoid that because that's
Mhm.
something that can come in later. But look at the domain, application, and the value that may derive out of this.
All right, all right. Yeah,
Yeah.
yeah. Okay, so I have discussed till this point where we have created this lattice optimized implant when we have done the validation. Next one is checking the manufacturability of this implant. So for that we have this build preparation capability where we can study the orientation of this implant on the build plate, and we can understand on different aspects like the amount of build time, the distortion of this implant after the print, the amount of support structures, and so on. And we can also do part nesting kind of study where we can print multiple implants at one go on the machine. So you can see this orientation study here. So this implant is oriented in different ways here on this base plate, and both have different things like in one orientation you will have your build capacity as high but manufacturing time is low, whereas it is opposite uh, at the other end. So you can do this kind of study here, the orientation study. Next one is to understand the stresses and the distortions on the designed implant or lattice optimized designed implant. So you can understand the stresses and the displacements here by doing FE simulation on that. Now, once the implant is manufactured, you can also manufactured by AM process, you can also compare the tolerances of the newly designed implant and your original CAD basically. So you can see the tolerances here, and then you can go for the validation where you can do some uh, testing here. So I'll show you that what kind of test has been done on this implant here. So this validation is done based on this ISO 7206 standard here. We have where we have applied a contact force near the hip of 2300 Newton by this plate here, and we have given some contacts between this stem and the femoral bone, and we have done the FE analysis here and to understand the fatigue life of this femoral stem here. So all this validation is done based on this ISO 7206 standard, and based on that, we have seen the stresses, the area at the implant where the stresses are high, and there is chances of failure, and we have also seen the number of cycles this implant will withstand. So by doing the fatigue analysis here, so this ISO 7206 standard is used for doing the life cycle prediction of this implant here.
So, Dr. Vikas, just to add, Satyam, so this is what I was trying to explain, that when we'll go to FDA, for example, we are doing the spinal implant. So they will ask all these questions. Do you satisfy ISO 7206, F1717? So all these things can be digitally validated, but will FDA approve it just because it's done digitally following a certain process? So then FDA also approves those digital processes, which we are working on, let's say, non-additive ones right now, but we can also do the same thing for the additive ones because there the process also comes into play, as you rightly pointed out. So these are the things which ANSYS is very intricately working and uh,
So,
with
when
FDA
we
and
have to
other.
partner with companies like you, definitely all these things, once they fall in place, it becomes very easy for Mr. Banerjee to take a call, because ultimately
Yeah,
we just cannot print a femoral stem and give it to the doctor to put it in a patient, There has to be
exactly,
large number of compliances that it has to go through.
exactly.
Yeah, so here
Yeah,
what
go
we
ahead.
provide is yeah, sorry. Here what we provide is the tool set and the process and methodology for making the FDA approval process easier. What basically FDA looks at is the repeatability, 100% repeatability with the same parameters, the results are the same. Once we establish that, then the FDA looks at, certifies the simulation process and takes that as for approval. So that's what I learned my engagement with the earlier company. So this is where our team is working, establishing ANSYS simulation methodology and process, because every company has a certain way of doing it. So what we are doing is we're working with FDA to ensure that this methodology is as acceptable by the FDA. However, additive and other stuff, although the ownership of the FDA will remain with the company that wants to acquire the FDA approval, ANSYS will work very closely to help and enable that to happen.
Exactly. That is what we are looking at.
Yeah. Yeah, go ahead, Kumar.
Yeah, thank you. So this is about the validation. So I'll just quickly summarize what I've covered. So uh, I think by now you have an idea that what we can do with our tool. So this is an end-to-end workflow from your material analysis to your initial design, and then doing your lattice optimization, then validating your optimized design, and then checking the manufacturability of the part here with the AM simulation, and finally validating the new designed implant by doing this ISO standard kind of testing here with our simulation tool. Yeah, so quickly I'll just show you one more case study here. So here I'll not take much time, but I'll just show you quickly that what else we can do here. So this is an example of a cranial implant here, where this cranial implant is manufactured using additive manufacturing process. So where we have done some detailed thermomechanical simulation to understand the manufacturability of this uh, implant, and later we have check the performance of this implant by doing impact test on this implant. So we have done a impact test where a ball is hitting this implant, and we have understand that what are the stresses and the deformations occurring at the implant because of this kind of impact. So this is again all the FEA process which is involved in this. That is modeling the implant, and then discretizing it, and then giving the different boundary conditions for this impact here. Uh, so this ball has been hit with 30 meter per second speed here. So and at this cranial implant center here. So because of this kind of impact, what will happen, or so that kind of things also you can understand by doing a FE analysis here. So we can see that because of this ball hitting, these are the areas where our stresses would be high, and we can see whether our implants will fail or it will pass because of this kind of fittings. So all these kind of scenarios we can model in FE, and we can understand that how our implants are going to behave for different type of loading conditions. Yeah, and I think we have a page also, Ansys Healthcare page, where we can find more case studies and articles related to healthcare engineering simulation. So you can refer to this website here for more detail or more article related to healthcare. Yeah,
Where's your
that's it.
company based out?
Yeah, so it is based out of Canonsburg in US. Here in
So
India,
headquarters
we
is
have
in,
centers in different cities like Bangalore, Pune in north side. We have in Noida, Hyderabad, Chennai.
Yeah, Dr. Vikas, our head office is Pune, registered office is Pune, and Pune will be the main office that we'll be interacting with. So all of us, myself, Anil, Dilip, myself, we are based out of Pune. Kumar is from Bangalore, right?
Yes.
Yes.
Yeah, so all the things that Dr. Shibu will be in touch with me. I'm the point of contact for all the healthcare initiatives. So it will be the team from Pune which will be addressing all the discussions.
Sure. Mr. Banerjee can also have questions.
Yeah, thank you very much for the wonderful presentation. Now, how can we take this forward?
Yeah, we're not done with the presentation yet. We are only looking at the additive part of it. We also talked of the biomechanics, how different patients. So I did hear discussions where there will be different ages of the patient, different porosity of the bones, different weights of the sizes and shapes of the patients who will be using it. So we also have simulation tools to basically uh, like you talked about, instead of modules, customized implant, we can talk about customized simulation based on these demographics and parameters. That simulation is something that we can cover. However, if you are not pressed for time, way forward is that we can have one more session. In fact, if it is okay, we can have a separate session detailing all our healthcare. Maybe you will pick up some few ideas that may be beneficial to you. And then the other option is we would like to have more details and a couple of more interactions with you and your team before involve our global teams, because when I ask for resources from the global, they'll have many questions, and I want to be prepared with those answers.
But Murli, what we can do, can we show glimpses of what we have in the overall view? We will not explain in detail, but then based on that, we can go into the detail.
Yeah.
Hmm.
If they have about 7 to 8 minutes, we should run through it because we've prepared that for them.
Is that okay, Dr. Vikas?
I'm okay, but I think Mr. Banerjee had to go somewhere at around 5. So if he's okay, I don't mind.
No, not we will not take more than 5 minutes. Just you show them what we are offering in ANSYS
Sure,
for the
sure.
Yeah,
healthcare equipment.
please go ahead.
Please
Go
go
ahead.
ahead.
Can I present, or maybe can I present your screen?
Yes, please go ahead.
I think you will have to raise a request for presenting. I don't know how it works.
Can
Yeah.
I?
Yeah, you
Is
can
it
present,
visible?
please. The same screen. You just need to put your presentation slide, just as you did earlier. So that takes care.
Can you see my screen?
No,
No,
Dilip, just put in your PPT on the same screen where this.
yeah.
Yes,
Yeah,
now we
now we
can.
can see you. Yes.
Now we can see.
Oh, so I'm just showing the glimpses. I'm not going into the details. At least, we want to show you now what offerings we are making in healthcare equipment. So this is the agenda, I think, and I'm not going into the details, but some of the drivers, I think you are already aware of why people are putting a lot of emphasis on either simulations or physical testing for healthcare industry. Every country is investing heavily on the healthcare industry. So this is already you are aware of more. And now we are talking about this V system. So this is a common system which can be applicable to any industry, but biomedical industry also it is very important. So right from the they call it like a verification and validation. So verification stage you can start with the requirements and you can go to the detailed design optimization later. So what is important here is from any simulation perspective is suppose if you are doing any physical testing, sometimes in the right side of V when it is failing in the validation. So you may need to go back to again the left side of V and making those design changes and doing the process again. It's a very expensive physical testing process. Some of this can be included in through the simulations. This is the message we are trying to pass through this V cycle. Similarly, from the medical engineering simulation perspective, I think from the any orthopedic implants or anything, what we are doing from the simulation perspective is now you can take the actual patient geometry and scan the geometry, and then from the scanned geometry you can create a model out of it. And once you have the model ready, if you can define those material characteristics in our simulation model and apply the actual physical situation and see how the implant is working, and see what changes can be made, where does it stresses more. Those iterations can be done and do the simulations. So this is where ANSYS can help you out to make your designs optimized, and later you can go for a physical. Instead of going at a different stages of physical testing, you can go for an final prototype where it is optimized design and go for a physical testing and get the approval done by FDA easily. So in this process, we can also definitely help you out. So now I'm just quickly go through now. I think in the interest of time, just showing these are the some of the areas we are already working with customers and see. So we are doing it in our software. This and similarly we were discussed about this in vitro testings and in vivo testings has been there since long time. We were today talking about in silico testing, which is a digital methodology. So here, so this is a computer molding and simulations. What roadmaps we have and what all the benefits you can get by using the this in silico approach. Similarly, we have orthopedic. We have many solutions available, be it a shoulder, elbow, spine, pelvis, hip, wrist, or femur, or knee joint, ankle. We have solutions available. So through ANSYS, you can develop a methodology and run the analysis, including optimization. Similarly, we have solutions for cardiovascular as well, not only orthopedic. So people are also using our solutions for respiratory and even in pharmaceutical process like drug delivery or be it a powder coating, crystallization, spray drying, and these are the some of the simulations where we have solutions. And even hospital supplies is a eye laser surgery or some of the dry powder or tubing, even including somebody like incubator or infection spread through hospital wards. So you can have the some of the simulations using our solutions. Even for we have solutions for diagnosis. Already you were talking about Medtronic. This is a case study already been done through using Medtronic only. So this has been given by them. This is already been available. So if you want to more details about this, we can discuss. And we also have a different simulations for completely from development stage to the regulatory approval. So you can see the be it a stunt designs or be it a blood pumps, spinal implants, some compliance is already being made. So using our solver, so we can have these discussions. Similarly, how we are building somebody today is talking about digital twins of our artificial intelligence for health, and that is where we can also deploy such a digital twin and including all the ecosystems because it's creating digital twin is not only ANSYS and only ANSYS inputs will not help you to predict the going to the closest digital twin. Sometimes we have a open architecture. We are ready to partner with different companies to come up with a digital twin products. So architecture is also open. So this is where one idea where we can also collaborate with universities, labs, everything, and we can ANSYS is a part of it, and then we can develop the methodologies. So this is the open architecture what we are talking about. We are only not only ANSYS expertise, we also have partnership with other different technology partners and provide a solution to it. So similarly, we have not so this is how we this is digital complete. This is a healthcare digitalization. So this is an insulin pump. So right from the complete, it's like a smart product which is having a hardware as well as software components associated with it. So we can develop a complete framework for this type of simulations. Similarly, you have a digital controllers, and we have a different even artificial intelligence and even a virtual organ. So you can see the how the drug delivery is going into the last part of your lung and see how it will use. So we have a different clinical test trials, different apps are available, and you can have a digital twin, so which we were talking about, and implantable antenna and medical devices. So what I can say here is, we also have something like a compliances testing is already working with policymakers to make sure, so it can be integral part of their testing process. So I'm just giving you the glimpses. So what we are offering ANSYS. So based on this, we can so we have solutions available. We are ready to have those discussions for subsequent during subsequent sessions. In the interest of time, I just quickly wrap it up, and we can have a detailed discussion. So this is because we have ANSYS have a different complete set of solutions available. But it's not, we are not only, because in a medical industry it's not about answers. Sometimes you need to partner with institutes and academics and regulatory boards. So we are open to that architecture to give you the solution about. So this is what I have quickly. I just gonna go through the different aspects of the solutions
Thank
what we are
you.
offering in the healthcare equipment.
Thank you, Dilip. Thank you so much. Excellent.
But you went so fast. I think you have a huge area to explore, and I
Right.
mean, it is not even the total one day affair that we needs to go through each and every aspect of your digitalization.
We
Yeah,
can,
sir.
Hello.
And
Yes,
Yeah,
sir.
we can.
we can meet them face to face, to actually understand the synergies, where they could be of a great help to us. I think Dr. Shibu can enable the face to face meeting
Sure,
also.
sure, sir. We will do that.
Yeah, I think we
I
would
think
prefer
I
that.
think there's a lot of things that can be discussed, and we can start off together uh, by making a consortium, because there are so many questions that are there. I don't think can be addressed today at this time
Exactly,
of the
yes.
day.
Dr. Shibu, my suggestion is that if it is fine, we would like to have these face-to-face discussions. Maybe either, I mean, the team can come to Pune, we can go there, or we can meet wherever that is required.
No, what I would
That is
suggest
not.
is, no, Murli, what I would suggest is you should actually visit their site. It's a beautiful factory, and the plant with such a beautiful. I mean, they are well structured. You will also get an idea in terms of, see, they also manufacture these modular implants, so you'll get an
Yeah,
idea.
we would love to see that, Dr. Shibu, because
Yeah.
while Kumar Satyam was presenting, one of the things I realized is he presented hip joint and he presented cranial implant. Both these are, I'm a user of it. One is my father and second one is by me. So I would really love to go and see how these things are made. We would like to be guests at his at Orthotex facility. So we are fine to go there. Multiple interactions, but what is not covered in our presentations is a lot about the devices. We have not covered
Right.
about devices because whether you talk about GE, Siemens, Philips, they use our solutions, various solutions, right from MRI scanners to medical imaging to lot many other things. But then that would make this subject quite a lot. So we try to focus something that are very near to your area.
No, no, only those aspects in terms of medical devices is a separate discussion. I will want to discuss with you separately also in terms of how we can explore as a possibility. But where I'm coming from is for Orthotech. Orthotech is now looking for 3D as one of the key areas of specialization, and also being the first initiator is critical in terms of this particular area, because modular implants they've always been one of the leaders. So what I understand is there are so many orthopedic appliances that can be really made ventured through a platform, and with the kind of solutions that you are offering, it can make more things easier. But very, very important is the validation process and everything. You need to fit into all those areas of requirements. But yeah, so we will also be consciously working with Orthotech to see that how we can also facilitate that. But at the same time, you come with your expertise in terms of what is offered. But yeah, so a physical meeting, Sushantji, at your convenience, and Dr. Vikasji, let me know. So we fix up a day and time. Accordingly, then we will take it forward. Whatever. I leave it to
Yeah,
your guide.
absolutely. We don't mind. We'll be happy to welcome them to our factory.
Yeah, yeah.
So where is it? Where is the factory, sir, or your
It's at
office?
Valsad, near Mumbai, 200 kilometers from Mumbai.
No, no, we are aware of Valsad. Many people from my own team are from Baroda, Ahmedabad, places. So
Okay.
that's fine. We can come to Valsad.
Most
Yeah, we can
welcome.
plan. Maybe after 15th of October.
Yeah, we will make it after 19th or 20th because our global CEO is in India. He's in India during 15th to 19th time frame, 20th time frame. So we will all have to be there. So October, either it's before October 16th or after 21st or something like that.
Sushantji,
Yeah.
I am there on 12th evening. I am there on 13th in Pune.
Okay.
Why don't you join me? And then maybe we can meet them in Pune first initially, and then they can come to the factory in case, because I am anyway in Pune for my visa.
Okay.
Let's see.
Let me
Let's see
see.
what we can.
I think that's a good idea. The reason is I could only gather 3 to 4 people. I had a very short notice. We have many more people who can join with their expertise in the Pune event. And then relevant people can then travel. Definitely, we would like to meet Valsad and CEO plant. So we can have both of them. Let us know. Since I don't
Immediately,
have the
I'm in Pune for some other work, but maybe 1.5 hour of meeting is possible. I'd just love to have Mr. Sushant joining me. If he's even if he's not been able to join, I can do. We can understand some dynamics when I'm in Pune. No problem. And then you have to come down to Valsad.
Yeah. But I think 1.5 hour would be injustice. My suggestion is keep at least 4 to 5 hours, because if you have a visa interview, I know which location that would be, but for you to travel to our office itself will take about 1.5 hour one way.
Oh, okay.
Yeah. So, but I would suggest if you can even extend by a day. I leave it to you, sir. I don't have your coordinates. If Dr. Shivu can just connect.
Shibu, yeah, Dr. Shibu can do. But see, major discussions can happen only when Mr. Sushant is there along with me.
That's
From an
fine.
orthopedic surgeon point of view, maybe a lot of inputs is what I can always do that. But from the medical device manufacturing, all the inputs have to be simultaneously shared along with Mr. Sushant. So that will be very important.
Yeah. Yeah. Let me check, Dr. Vikas.
Huh.
I need to check and I'll come back to you.
So that call we can take at some time. I think Shibu, I think you can also do some form of coordination for all of us.
Yeah. We'll do that. Yes, definitely. So we will make that possibility if everybody's convenience to see that. No, we can.
Sure.
So thank you so much, gentlemen, and thank you, Dr. Vikas and Dr. Susanji, and also
No,
Murli. Thank you for your time and your
Thank you. Thank you very much.
presence,
we would love
Kumar.
to thank ANSYS. The entire team is here and they really made a good presentation.
Yes. And to the
Thank
team,
you.
thank you for the various applications that it can touch upon. That's really interesting to know that all it can be of great
Yeah,
use.
there is a lot of applications. In fact, I have seen ANSYS program somewhere and we did our product, validation somewhere else.
Yeah,
So I am aware of ANSYS.
right.
Thank you
Great,
so
sir.
much.
Thank you
Thank
so much.
you.
Great,
Thank
great
you,
to
sir.
know.
Thank you. Bye bye.
Thank you.
Thank
Thank
you.
you.
Yeah,
Thank you
thank
all of
you,
you.
everyone.